Without further ado, we'll introduce our moderator for today, Eloisa Acha. She is the Director for Research Relations at the Cockrell School of Engineering at UT Austin. Take it away, Eloisa.
Hello, good morning, everyone, and welcome to our next series of the TED Talks. Dr. Filippo Mangolini is going to be our speaker today, and I'm very pleased to announce and talk to him and talk about his background this morning, and then hand over the microphone to him so that he can have a conversation with you about his research. And towards the end, we'll have a Q&A session. Dr. Filippo Mangolini completed his university studies at Polytechnic University of Milan in Italy in 2006. He then received his PhD in material science at the Swiss Federal Institute of Technology. And after obtaining his PhD, Dr. Mangolini conducted postdoctoral research first at the University of Pennsylvania and then at École Centrale de Lyon in France. Between 2015 and 2017, Dr. Mangolini was a university academic fellow at the University of Leeds in the UK. In January of 2018, Filippo joined the University of Texas at Austin as assistant professor in the Department of Mechanical Engineering, Material Science and Engineering program. Dr. Mangolini's research group focuses on the development of physically based understanding of the structural transformations and chemical reactions that occur on material surfaces under extreme environments. And without any further ado, I will hand over the microphone to Dr. Filippo Mangolini.
So good morning, everyone. Let me share my screen. Can everybody see that? Yes? Good. So good morning, everyone. It is a great pleasure for me to give this seminar today. First of all, I would like to thank Eloisa and her team for putting this together and providing me with the opportunity to share with you some of the work that we have been doing more recently. So before going into the details of what I'm going to talk about today, let me give a very broad overview of the problem that we are trying to address here. As you may know, the durability of material constitute or constrain engineers when they design novel technologies across several sectors, from manufacturing to the automotive industry, to aerospace, to microelectronics. And to address those challenges, we have to develop new materials that can withstand the extreme environments and conditions that some of these devices have to experience during their lifetime. As a particular and concrete example, in this slide you see a jet fighter, and highlighted in the jet fighter are some components that are either exposed to extreme temperature or they have to withstand extreme conditions. For example, the thrust vector on the backside of the jet fighters. If you think about also other kind of aerospace satellites, you see that it's not only the temperature that have to go from very low values to very high values, but also the condition, the extreme environmental condition that these components are exposed to, they vary widely in space. So for example, from ultra vacuum to oxidizing environments, as well as moving components. A lot of the components that are highlighted here, they do have surfaces that are in relative motion, meaning they're sliding against each other. That's exactly one of the interests of my research group, which is tribology. For those of you who are not familiar with the word, tribology is the science and technology of interacting surfaces in relative motion and associated subjects, mainly friction, wear, and lubrication. When two bodies come into contact at the macro scale, contact occurs at the level of single asperities. These asperities have the dimension of a few microns or even a few nanometers square. The usual way I introduce this to my student is by thinking about putting Austria upside down on top of Switzerland. Of course, you have mountains coming into contact because of surface roughness. And it is exactly at the level of these single asperities that fundamental phenomena occurs, including plasticity, elastic deformation, fracture events, and the conditions are so extreme in terms of temperatures and in terms of out of equilibrium condition that you can also trigger chemical reactions. In other words, tribological surfaces and interfaces are an interaction, a complex interaction between chemistry, physics, and mechanics. And I will get back to the importance of studying these nanoscale features later on in my talk. Why do we care about tribology? Tribology has a profound impact on our economy, lifestyles, and environment. More than 10% of the world energy produced is wasted to overcome friction and replace worn-out components. To give you an example, the economic losses due to friction, wear, and replacement of worn-out components is around 4% of the gross domestic product, so $740 billion in the US. To even being more concrete, around 1/3 of the fuel energy that is put in our cars is wasted to allow your car to move. So that means that every single one of you who owns a car is wasting something like $300 per year just to allow your car to move. So tribology has a direct economic impact overall, but also in our everyday life. But it's not only economic, it's also environmental, as well as I will touch upon later in this talk, healthcare. More recently, there was a report to ARPA-E by Karpik and Lee that highlighted how much research and the importance of research, fundamental research and applied research in tribology to address these important global challenge. So as I posted here, a total of 20 crores of energy could be saved through technology enabled by research in tribology. So it's a gigantic amount of energy that we can save through targeted research. And that's exactly what my research group is trying to do at UT Austin. So what is our philosophy? In general, our philosophy can be conceptualized through the material science tetrahedron, which highlight the required interdisciplinary study of material synthesis, structure, properties, and functional behavior. Our approach, though, is not the traditional approach that is used in material science and tribology, where you have a systematic parametric study between the relationship between material synthesis and functional behavior. Rather, we want to establish synthesis, structure, properties, functional behavior relationship, meaning we want to establish the knowledge necessary for rationally designing materials. And we want to address that problem by using advanced surface analytical methods and in situ approaches to investigate in real time in situ what happens when surfaces are in contact and they're sliding against each other. So again, the aim is really to provide guidance for the synthesis of materials that have enhanced behavior and then can lead to the development of a new range of devices that can have enhanced tribological performance, so they are more energy efficient, they are more wear resistant, and then they can allow to enhance sustainability by reducing the impact of tribology. And this, of course, can lead to novel technology across different sectors, across different length scales, from the micrometer, nanometer length scale to the meter length scale. And I will get back to this at the end of this talk. So the research project that we are working on in my lab can be divided into 4 main categories. The first one is liquid lubricants. I'm trying to understand the origins of the molecular origins responsible for the tribological response of lubricants that are used in engines, but also potentially in aerospace applications. Thin films, again, mainly for aerospace application, but also for microelectronics, bulk materials, and finally, a project on tribal corrosion for the healthcare. Today, I will mainly focus on liquid lubricants, but we also mention something about ongoing research on thin films and tribal corrosion. Let me start with the first topic. As you might know, our engines, internal combustion engine, rely on an hydrocarbon fluid to enhance the lubrication or to lubricate moving components. This lubricating fluid consists of hydrocarbon, base oil, and an additive package. The additive package consists of several molecules, each of which has a specific function. Among them, we are interested in investigating anti-wear and friction-reducing molecules that, as the name says, reduce friction, so enhance the energy efficiency of the internal combustion engine and prevent damage of components sliding against each other. What is the problem? In the last 20 years or so, exhaust after treatment systems have been introduced to reduce the toxicity of exhaust gases. However, these catalysts, they are easily poisoned and through deposit on this catalyst material by byproducts of components that are usually found in engine oils, and in particular molecules that contain a high level of phosphorus, sulfur, and metal ions. Because of this problem, international legislations are trying to reduce the amount of phosphorus, sulfur, and metal ions in engine oils, and they are also trying to push towards molecules that are highly thermally stable. One of the potential additive that has been quite widely investigated recently is a family of liquids which is called ionic liquids. These are liquids or salts that have melting temperature below 100 Celsius. They are composed of an organic cation and a small coordinating anion. They have unique properties such as high thermal stability, negligible vapor pressure, and good ionic conductivity, which make them attractive for a number of applications, from green solvents to separation media, as well as working fluids, for example, in lubrication. They have been shown to lubricate even difficult to lubricate materials such as silicon and light alloys. They are, of course, a candidate material for engine oils, but also for aerospace application, given the low vapor pressure. One of the problems is that there are 10 to the 15 ionic liquid available due to the number of permutations between anions and cations. Of course, I can try to have 10 to the 18 graduate students, but probably that would not be the most efficient way to address this problem. So what we are trying to do is to understand the underpinning mechanism by which ionic liquid can lubricate materials. So what is known? So if you take a very rudimentary picture of what's happening when macroscopic bodies come into contact and slide, because of surface roughness, you have these asperities that come into contact. And this is exactly where a lot of the interesting things happen. So what happens when you put this nanometer scale single asperity into contact in the presence of the ionic liquid? This a very simple problem you might think about, but is actually very complicated and challenging to address. A lot of people use nanoscale devices, such as the surface force apparatus and the atomic force microscope, to squeeze the ionic liquid between the surfaces, trying to understand what happens between the ionic liquid when they are confined between these two solid surfaces. So published literature show that when you have velocity equals to 0, meaning that they are static, you're just compressing the two surfaces and confining the ionic liquid, you have what is called progressive squeezing out of the ionic liquid. Here you see the force experienced by the surface when they come into contact with the reference surface here, the bottom one, as a function of separation d. And what you see is exactly some fluctuations. These fluctuations, or discrete steps, correspond to the squeezing out of ionic liquid during the progressive decrease of the separation between the two surfaces. So in other words, the ionic liquid organize themselves in layers where you have an excess of cations and an excess of anion. And when you're decreasing the separation, you're progressively squeezing out slabs, electroneutral slabs, so you're removing anions and cations at the same time. And because of this squeezing out, you have these progressive, discrete steps in the force separation curve. Because of this squeezing out, or because of this rearrangement, people have basically proposed that this arrangement of the ionic liquid during the compression and confinement actually results in the lubricity of the ionic liquid. However, at the macro scale, a group led by Jun Kyu from Oak Ridge National Lab clearly showed a while ago that ionic liquid actually react on surfaces, so completely different mechanism. They create these layers, which you see on top of this steel. At the bottom here, you have steel, and then you have this tribal boundary film. And what researchers from Oak Ridge showed is that in the case of this phosphonium phosphate ionic liquid, you have the formation of this phosphate-rich layer that actually prevents wear and leads to low friction in macro scale tribological experiment. So clearly here that we have a length scale problem. So at the nanoscale we have some information, and at the macro scale we have some other mechanism coming into play. So that's exactly what we wanted to do to start with in my lab. So what happens really when you're applying very high pressure at the nanoscale with the phosphonium phosphate ionic liquid? What is the underpinning mechanism of ionic liquid, the lubrication mechanism of ionic liquid, and can we understand at the nanoscale what happens at the ionic liquid itself when it is squeezed at a very high pressure? How do we do it? We use, as I said, in my group, we push the boundaries of state-of-the-art analytical methods, and in particular, in this case, atomic force microscopy. Why? Because atomic force microscopy allows to perform in situ tests in single asperity sliding contacts. For those of you who are not familiar with AFM, AFM uses a flexible cantilever, at the end of which you have a very sharp tip that squeezes together or pushes together, that are pushed together, and you can achieve extremely high load and pressure in the presence of the ionic liquid. This would allow us to show or to understand and visualize what happens at the contact in real time, while knowing basically the shape of the tip, meaning the pressure, to have an accurate measurement of the pressure. The test that I'm going to talk about, again, in the case of phosphonium phosphate ionic liquid, which is a well-known ionic liquid pioneered by researchers at Oak Ridge, we basically perform high pressure, very high pressure, the highest we can go with AFM in this dark red region. And every now and then we zoom out and we visualize what happens in this small area down here. So let me go to some of the results. At the top, you see the topography image, and at the bottom, the friction image, which is acquired at the same time with our AFM instrument. The dark red dash area that you see here is where we increase the load to the maximum load that we can achieve with our AFM. So if we slide for 350 frames, the part in the middle, and then we zoom out and we take a new image, that's the second image that you see here. What you see is an area which is slightly darker, meaning that has slightly lower height. In other words, we are removing materials. At the same time, we see a darker region in the friction force, meaning that we are decreasing the friction force measured by AFM. And again, we can increase the cycles in the inner part of this image, where we apply very high load. So we perform 650 cycles inside this area dashed in red. And again, we are removing more and more material. So there is a progressive removal of material, and at the same time, we also have a decrease in friction. The area that was scanned at high load was actually getting much more smoother as measured by RMS roughness. So we try to quantify this, and by computing the height difference between the area scanned at high loads and basically the reference area that was not scanned at high load. But we also computed the change in friction by looking at the friction force distribution and computing the difference between the distribution in the region that was loaded at the maximum load and the reference area. The key results in this plot at the bottom right, where you see the change in friction as a change in height. And what you can see is a slight progressive decrease in friction until 4 nanometers, you remove the first 4 nanometer of the surface. And this is a value that has been comparable or was comparable to the native oxide layer on steel, meaning that once we go through the steel oxide, we achieve a low friction steady state regime. So what is the origin of this? So as a surface chemist, I'm always interested in spectra. I'm always interested in understanding the underpinning surface chemical origin of friction changes. So for addressing this problem, we have to use a facility, a national facility, the National Synchrotron Light Source. It's basically taking a sample which is 1 square centimeters and finding a spot which is on the order of 10 to the minus 8 centimeters square. So my student very patiently went and traveled thousands of miles and was able to see a 2 by 2 microns region over a 1 centimeter square sample in a very effective way in a few days at the synchrotron. I'm going quite quickly in this slide for one reason, and I will clarify that in a moment. But basically, we were able to acquire X-ray absorption and X-ray photoemission spectra inside the region scanned at high load and outside. And as you can guess, there is not any significant difference. I'm not going to talk extensively about what all these spectra are. The main take-home message is that there is not any significant difference. And XPS, careful XPS analysis that we did show that actually there is both cations and anions absorbed on the surface with a slight enrichment of the anions on the surface. So clearly these results show that there is no stress-assisted chemical reaction. So there is no stress-assisted chemical reaction leading to the formation of a film. The ionic liquid is absorbed as it is on the surface. So this seems to be in contradiction with what was reported in the literature. But after modeling the temperature during the sliding experiment, we understood that in our case, we have a very minor change in temperature at the contact during sliding, during AFM. So our contact pressure or our contact temperature during our experiment is still the bulk temperature. Whereas in the case of the experiment reported in the literature, since they were sliding at very high speeds, there was a drastic increase in the contact temperature, which results in a temperature that is very close to the degradation of the ionic liquid. So the stress in the case of the experiments reported in the literature probably is enough to lead to the reaction of the ionic liquid on the surface and the creation of a boundary layer. Being surface analysis people, we were also interested to look at the molecular fragments in these boundary layers. And what we show is that actually we have in the region stress at very high loads, we have an enrichment of the anion, the phosphate, while we don't have an enrichment of the cations, a small enrichment probably. So all these changes were also correlated to changes in surface potential that we measure by low energy electron microscopy. So the low energy electron microscopy measure the surface potential by looking at the intensity of reflected electrons as a function of electron energy. The inflection point here is a clear indication where the surface potential of our sample is. And what you can see in this slide is a clear difference between the IV curve extracted from the region outside this highly loaded scan region and the region inside, meaning that the region inside where we apply high load, there is a completely different surface potential. So how can we put all these together? We could put all this together thanks to density functional theory calculation, which were done by looking at the absorption of phosphate ions on iron, metallic iron and iron oxide. Of course, there is a change in enthalpy of absorption, but the key point here is that phosphate on metallic iron interacts through multi-point interaction of oxygen atoms with iron, whereas phosphate only binds through a monodentate, meaning this only through an oxygen atom on iron oxide. So based on these, our results and the DFT calculation reported in the literature, we came up with these proposed models where we have mainly phosphate absorption on iron oxide. As the scanning tip slides at high pressure, we are starting organizing the ions through lateral confinement, something that I'm not going to talk about today. If we slide at extremely high loads, we go through the oxide, which results in a difference in the way in which the phosphate ions binds to the surface. In the case of iron oxide, you have only monodentate configuration, whereas in the case of iron, metallic iron, you have bidentate configuration, which thanks to the surface being extremely smooth and the lateral confinement of the AFM tip, the arc change basically maximize the interaction energy, they reduce the configurational entropy, and they form this densely packed layer, boundary layer, that is helpful in reducing friction. So again, in this work, we show how you can combine in situ AFM and advanced spectroscopy to understand the mechanism of action of ionic liquid and how they can lubricate surfaces. So again, atomic force microscopy can be used to evaluate the processes occurring at steel surfaces. I showed that there is a significant reduction in friction after you remove steel oxide or the oxide layer. There is no stress-assisted chemical reaction, so there is no boundary, really inorganic boundary layer formed here. But we have the formation of a densely packed surface layer made mainly of phosphate ions once you remove the oxide layer. So this work was recently published in Advanced Materials Interfaces. For those of you who are interested, please refer to that. If you don't have access to the journal, please let me know. I will be happy to share the paper with you. So very briefly, in the last 5-10 minutes, I'm going to touch upon a couple of projects. One is about doped carbon materials, and the second one about tribal corrosion. This work, first of all, was a collaborative effort between University of Pennsylvania, École Centrale de Lyon, University of North Texas, and University of Florida, with a contribution from NASA. For those of you who are not familiar with the term Diamondlike carbon, Diamondlike carbon is a very well established class of thin film materials whose success derives from their attractive physical, chemical, and mechanical properties. They consist of an amorphous network of carbon atoms, and because of their attractive physical, chemical, and mechanical properties, they have been used as coatings for automotive components, for machining tools, for aerospace application, as well as for biomaterials, including total hip replacements. However, there are two major limitations that currently hinder the use in a wider range of applications. The first one is the limited thermal and thermo-oxidative stability, and the second one is the environmental dependence of friction and wear. We have done extensive work also on the second topic. Today, I'm only going to focus on the first topic. So as in the semiconductor industry, if you introduce new elements, you can actually tune and tailor the properties of diamond-like carbon materials. So here you see a lot of work that has been done in the last 20 years. And today, what I'm going to focus on is the effect of silicon and oxygen. Because silicon and oxygen have been shown to increase the thermal stability, but the origin behind it was not established. So that's why we started looking at this DLC that includes silicon and oxygen atoms. We call it amorphous carbon, hydrogenated carbon with silicon and oxygen. And we have done extensive work in the last five years looking at these. So we coupled advanced characterization method that synchrotron facilitates, including Nexa spectroscopy, X-ray absorption spectroscopy, and molecular dynamics, trying to understand the origin behind the higher thermostability of this material compared to the material without silicon and oxygen. Here you see the fraction of carbon in sp3 configuration as a function of temperature. These are MD simulation. And what you can see is that the material without silicon and oxygen in gray undergoes much more transformation or increase in sp2 fraction. Sorry, this is sp2. Much more increase in sp2 fraction. When you increase the sp2 fraction, you have a transition of sp3 to sp2. You usually lose a lot of the mechanical properties of this material. So you want to keep the sp3 as constant as possible. Of course, these results shows that are confirmed also by experimental results that the introduction of silicon and oxygen render the material more thermally stable. And by molecular dynamics simulation, we could identify the origin, meaning that the material that contains silicon and oxygen have a lower fraction of strained carbon-carbon bonds, which are the first one they want to break. So as we can easily understand and visualize, if you have a bond which is strained, if you increase the temperature, the higher is the strain of the bond, the easier it is to break that bond. We were also very fortunate to participate in the materials on International Space Station experiment between 2012 and 2011 and 2012. Basically, this material was sent aboard on the International Space Station for a year and a half, where the material was exposed to thermal cycling, vacuum, and ultraviolet radiation, as well as, most importantly, atomic oxygen. Atomic oxygen is a great issue for materials on satellites because of its high energy as well as its the high flux. What we could prove upon retrieval of the sample on Earth is that this material has actually a self-healing, self-protecting behavior, meaning that the addition of silicon and oxygen prevents the material to be completely burned away. If you take the same kind of material without silicon and oxygen in space, they are quickly gone in a few seconds because atomic oxygen basically burns away the carbon in these DLC coatings. If you introduce silicon and oxygen, and these were really nice images taken by Tom Scharf at UNT, you have the formation of this 5 nanometer silica-rich layer, which acts as an oxygen diffusion barrier and prevents the carbon underneath to react with atomic oxygen and be completely burned away as carbon dioxide, basically. And these experiments were also confirmed by experiment we did in the lab, where we annealed the sample at very high temperature in lab environment. And again, we observe this self-healing, self-protecting way of the material to create this oxygen diffusion barrier for oxidation of carbon. So in the last 2 minutes or 5 minutes maximum, I'm going to talk about the last project that we are actually working on right now in my lab. As you know, arthritis is a big and has a profound economic and well as lifestyle impact on our population. And the usual way of solving arthritis problems is using total hip replacement. Of course, if you look at the market, there are different solutions for total hip replacement. But however, the average lifespan for state-of-the-art total hip replacement is only 15 years. And this is not a problem for some of the population that is a little bit older, but it can create really severe problems for younger patients that have to undergo maybe a second surgery later on in their life. The failure mechanism that limits the lifespans of these replacement is actually deriving from failure of these components, multi-components, due to the coupling between sliding or mechanical micromotion and corrosion. That's what is called tribo corrosion. So of course it is an environment, there's an over fluid, and you have also micro motion, and the coupling creates very much a lot of problem in terms of basically release of metal ions that can cause inflammation and pain in patient. So of course what we want to do first of all is understanding what happens at this interfacing, and by understanding trying to guide the design of new material that can prevent metal ion release and inflammation in the patient to increase the or to improve the longevity of these replacements. So these are preliminary results that we have. So we look at state-of-the-art material, cobalt, chromium, molybdenum, and in particular in this set of experiments we look at how this material repassivate in the presence of basically environment that contain or do not contain the bovine serum or the albumin that is present in our synovial fluid. So we coupled basically electrochemical experiments and measurement with sliding experiments. We could basically correlate friction and correlate the electrochemical potential, and whereas there's also the impedance spectroscopy measurement that we carried out. And what we could observe is that the kinetics of the repassivation of cobalt, chromium, molybdenum was very fast only in the buffer solution without any albumin. Whereas if you have an albumin, you have proteins in the buffer solution, the repassivation kinetics is much slower. And also the passive film was much more porous. This is an important problem to look at since it will also impact the mechanical properties of the passive layer and the potential wear resistance of the passive layer over time. How and why does it happen? We again we are a surface analysis group, and we perform preliminary XPS measurement on this, which indicated that the passive film, so the oxide film created on cobalt, chromium, molybdenum, formed in the presence of albumin, contain much less molybdenum, most probably because of the binding of molybdenum with the bovine serum albumin. Something that we are looking at now through the analysis of the liquid that is left at the end of the experiments. So with this, I would like to conclude. These are my final take-home messages. So today I showed you how we use atomic force microscopy and macro-scale experiments together with surface analysis and advanced surface characterization methods to understand the relationship between material synthesis, structure, properties, and functional behavior. So even though our research is in the low TRL levels, meaning we're we are trying to address basic research questions, the outcomes of our research can really lead to guidelines for designing materials and solutions for addressing problems, applied problems across different length scale, across different sectors from the micrometer, nanometer length scale in, for example, hard disk drives, to the meter length scale, such as in satellites or even in our automotive engines. So with this, I would like to conclude here. I would like to thank, first of all, the funding agency, the Welsh Foundation, Sandia National Lab, the Ralph Junior Enhancement Award, and the TAIO Tribology Resource Foundation, together with the UT Portugal Research Program. I'll leave you with my contact details in case you want to engage more and you have more questions in the future. And lastly, and last but not least, I would like to thank all my group members, especially Jichuan Li, who performed the experiments on the Ionic liquid, but all the other group members that I'm very proud and honored to have in my group for their hard work and continuous engagement in our research effort. So with this, I stop here, and we'll be more than happy to take any questions you might have.
Thank you. Thank you so much, Filippo. This has been a great presentation. And we do want to remind our audience again to type any question that you might have on the chat window. And we do have a couple of questions, so I'm going to go ahead and read the questions to you, Filippo. So the first question we have is, do you think the ionic liquids layer is just fissiosorbed then and totally dependent on the tip presence? So if the tip is withdrawn, the IL just gets reabsorbed by the fluid?
Yes, so there is a continuous, so in the case of the oxide, we have XPS data that very clearly show the absorption of the ionic liquid, and especially the phosphate on the surface. In the case of the metallic material, I don't think there is a continuous reaction or the continuous exchange reaction. I think it's first of all, the entropy of absorption is much higher, meaning that there is a strong binding between the phosphate ions and the metallic surface itself. So I think it's chemical option in that case. Eloisa, I cannot hear you.
Okay, so here's the next question.
Okay.
For you. Can tribal corrosion experiments be performed at the nanoscale using the atomic force microscopy approach showed in the presentation?
That's a great question. It's something that we are moving towards too. Our AFM has been, especially the liquid cells that we have in our AFM, have been designed and thought exactly for doing that kind of experiment. Those are not very easy experiments, but we do have the capabilities for doing that in the future, and that's something that I clearly would like to address more in the future, given that the atomic force microscope, as I showed you today, allow you to very carefully control the contact loads and to have a better understanding of the interrelationship between stress and chemical reaction at the interface. So yes, we can do it. We have not done it yet. Those are very difficult experiments, but I would love to do that in the future. So we are, to be honest, we are already set up for doing those experiments. We didn't have enough time yet.
Great, great. So another question here from our audience: what are the challenges in lubrication for electric vehicles?
Oh wow, that's a great question. So there has been a lot of discussion in that area. All the Tribology community is coming together and trying to figure it out, the challenges. From my own knowledge, the challenges are completely new, and that's why there are a lot of opportunities. The liquids that are put in the electrical vehicles, to my knowledge, they come into contact with completely different surfaces in terms of chemistry, but also you have the presence of high voltages or regions of high voltages, which can be a problem in terms of corrosion as well. So the coupling between corrosion and tribology, I think, will become even more problematic in the case of electrical vehicle, if that is the case. So there are a lot of papers in that area going on. So there are several challenges, including the presence of voltages in some of the area of the electrical vehicles.
Okay, so continuing on the engines topic. So another question: most ionic liquids are not miscible with oils. Is there any strategy for exploiting ionic liquids as additives in engine oils?
Yeah, another great question. So so there are two challenges. So there are two approaches. So one of the approach was tackled by Professor or Dr. Q from Oak Ridge National Lab, and that's exactly the ionic liquid that we have been using, the phosphonium phosphate ionic liquid. That was the first one, to my knowledge, that was proven to be completely miscible in the oil, and that was the results of very careful, very well thought planning of chemical synthesis. So we can work with chemists to try to make the ionic liquid miscible in the oil. So that's the first route. That being said, it's of course time consuming. It will require a lot of synthesis, and again we have 10 to the 18th or 10 to the 18th ionic liquid available, potentially available. So another approach that we are trying to explore in my group is actually to encapsulate the ionic liquid in polymeric shells, trying to have an approach similar basically to the drug delivery approach, where you basically encapsulate the surface active ingredient or the ingredient that you want, in this case the ionic liquid, in a polymer shell, and the polymer shell allows you to basically introduce much more ionic liquid in the oil that is possible theoretically. So to go beyond the solubility limit without having phase separation. And the polymer shell should break at the interface. That's something that is going on. That's the project funded by the Wells Foundation. Something that we have been working on for the last 2 years, and hopefully we will get a publication. We should have a publication by the end of this year on that topic. So that's the second approach we are pursuing. There might be multiple ones, but that's our idea, and that's what we are trying to explore in the lab.
Great, thank you. Filippo, can you comment more about the design of new materials for the medical components that you discussed in the last application? What are the materials that you're currently working or looking at?
So for the moment, so the project that I just referred to was really a fundamental project looking at passive layer formation, reformation, and chemistry, and the effect of proteins on that passive layer in terms of porosity, mechanical properties, and chemistry. So for the time being, we are really focusing at state-of-the-art materials, cobalt, chromium, molybdenum, that being, so for the time being, trying to address some of the fundamental questions that are in the literature. But in the future, I really would like to explore more materials, including coatings such as Diamondlike carbon, and even like polymers potential polymers on total heap replacement. So those are the two things that I'm envisioning going on in the future. But the same thing in terms of tribal corrosion. There are much more that we are planning to do also in terms of other application, given that tribology and corrosion together is becoming a big issue well beyond the medical field. So for the time being, coming back to the question, just cobalt, chromium, molybdenum, but moving forward, certainly we are going to look at other coatings such as DLC, of course, but also potential polymeric films on metals.
Great. Filippo, also, can you, here's another question, can you increase the temperature in atomic force microscopy experiments?
Theoretically, yes. We can go up to, if I remember our setup, theoretically you can go up above 300 Celsius. That being said, there are always challenges when performing high temperature AFM experiments, which is the stability of the AFM and the drift of the AFM. So that would require a lot of patience from the student just to allow the AFM to stabilize. It's totally doable. It just will require a little bit of time. Yes, but we are set up to go up to 300 Celsius. So we should be able to do it. And there are groups doing high temperature AFM for fuel cell research, going to even 400 Celsius. So it's totally doable, but there are significant challenges with those kind of experiments.
Right. So Filippo, I mean, the research that you're doing can have great impact in several applications in the industry. So I'm sure the audience would like to know, how could they potentially get involved in some of those projects with you?
And in several ways. First of all, again, our expertise lies in really surface chemistry, surface analysis, and trying to bridge length scale. So if you contact me, I will be more than happy to have a discussion. I can disclose more details of the work that we are doing, and start from there. So it's as we discuss problems that are of significant technological relevance, we can easily break down and try to address first fundamental questions that have a significant technological impact, and move from there. So again, I put in this slide my contact details. Don't hesitate to contact me. I'm open to working with more companies and to address problems that are of industrial importance.
Sounds good. I'll just read out the last question from the audience, and then we'll transfer over to a wrap up. Would you have gotten similar thermal robustness of the DLC if you had just capped it with a thin layer of CO2, or I guess SiO2, instead of doping the DLC with Si and O?
Yeah, that's a great question. So first of all, in aerospace, a lot of the polymers are undergoing similar degradation upon exposure to atomic oxygen. So Kapton is a clear example, and there is a lot of research paper on that topic. So the usual way in the aerospace industry they go around with that problem is by really putting a silica surface layer or aluminum surface layer to prevent the basically oxidation and removal of the polymer. So you can think about, and that's what the question is, we can do the same with DLC. Yes, you can do the same with DLC. The problem is that the thermostability of the DLC will not be the same. So as I showed you here, the DLC with silicon and oxygen is much more thermally stable in vacuum. So the presence of silicon and oxygen itself increases the thermostability in vacuum without any oxygen. So now there is a second benefit for this self-healing process, which is that this material, they have a quite good friction properties both in humid environment and in dry environment compared to undoped DLC, which means that when we are testing the material on Earth, you can still test without having high friction regime, and the material can work in space after it breaks through the silicon and oxygen layer. So the self-protecting surface allows you to basically retain or get a good friction properties on Earth, and eventually to go through a low friction regime even in space, and maintain and basically have the same DLC underneath, basically. So, but again, coming back to the question, the thermostability, it's basically in vacuum is much higher, or is not much higher, is higher if you introduce silicon and oxygen. This would not be able to happen if you put a silica layer on top of it.
Great. Well, thank you so much, Dr. Filippo, and I also want to thank all of the colleagues behind the scene helping us organize and put together this webinar for this morning. Now I will pass the microphone over to my colleague Canavis, and he's going to close this event for us. Thank you, everyone.
Thank you, Eloisa, and thank you, Dr. Filippo. We really appreciate you joining us today. And thank you so much for your outstanding questions. We want to formally thank each of you for joining today's webinar, and we hope the conversation was valuable. Next, we wanted to highlight a few of our professional development short courses and future webinars. As you heard from our speaker, lifelong learning and research is fundamental in preparing individuals to remain competitive in today's workforce. To support the needs of working mechanical and petroleum engineers, UT Engineering has created an online mechanical graduate certificate in controls and a petroleum engineering graduate certificate in data analytics, specifically built for the oil and gas industry. Both of these graduate level certificates are created for degree seeking and non-degree seeking students to provide them tools to optimize process and systems that you use every day. Perhaps you have not been in school for a while. Don't worry, we have streamlined the application process for working professionals professionals. So visit our website today to learn more about our simple application process. Good leadership is always needed in tackling some of the world's biggest challenges, as you heard today. We at Texas Engineering Executive Education have carefully created a certificate program that pinpoints tools and methodologies to tackle leadership challenges for STEM professionals. The last class in our series is still available for registration, so please visit our website to learn more. Next, we want to quickly highlight the upcoming energy-related courses with pipeline technology and measurements classes. If you or your organization need additional training in this area, please contact our PTEX department today. We also want to thank the 3 units of the Cockrell School of Engineering that helped put this wonderful program together. First is the Texas Engineering Executive Education, who works to reskill and upskill companies' current workforce, either through our master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education or training, make sure to contact our department to learn more. Next is the PTEX, the Petroleum Extension of Texas. This department has been around for over 75 years, serving the oil and gas professionals either through e-learning, publications, and online or in-person training. We have the training to meet your oil and gas needs. And last but not least is our research relations team. This team partners with industry to solve some of the world's biggest challenges in energy, water, transportation, wireless communications, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between companies and UT's researchers. So if your company would like to partner with Filippo Mangolini to explore additional research opportunities, please email the Research Relations Office to initiate a discovery discussion. All 3 units are here to serve you and your company through education, training, and research. So feel free to contact us at any time, and we would love to collaborate on helping you reach your company's full potential. As we continue in our Text Talk series, I want to make sure you're aware of our upcoming webinar. On October 23rd, Dr. Peter Stone, who is the head of the robotics lab here at UT, will be discussing learning and multi-agent reasoning for autonomous robots. This webinar will discuss how we address robots interacting with other robots, but more importantly, how do we build robots to interact with humans? With robots becoming more popular for recreation, business, and military, I know this will be a great discussion. We hope each of you would join us for the future webinar, so mark your calendars today. If you would like to provide feedback on today's webinar or suggestions for future topics that may interest you, please include them in the survey following this presentation. Once again, we would like to thank you for joining us today. We hope you have a great rest of the week, and hook 'em horns.